Let's now move on to understand multiple scalars, and in particular at some point we'll go to scalars in higher dimension. So we begin our discussion with two scalars. So two scalars in 0 plus 1 dimension. Okay, so the action describing two scalars in 0 plus 1 dimension is the following. So two free scalars. Okay, so we will we'll quantize the system following standard procedures. And the standard procedure is to impose canonical quantization. Okay, so pi j is now it's easy to determine the spectrum. Okay, so in the same from this we can define creation and annihilation operators just like in single scalar. Okay, and the way if we do that, then you can show that the creation and annihilation operators. So the definition of creation and annihilation operators is very similar to single scalar, and if you do that, then this is same as delta ij ai aj is 0. Okay, so the creation operators, also the annihilation operators and the creation operators, they are commute of the two different species. But the commutation relation between the creation and annihilation operator of the same species is just simply the identity which we already know. So from this the Hamiltonian is h bar m1 a1 dagger a1 plus half plus h bar m2 a2 dagger a2 plus half. Okay, so this is the spectrum. In the same way we can define Feynman propagators and other propagators. Let's just restrict to Feynman propagators. Other things follow in the same way. So the Feynman propagator is defined as time ordered product of, let's say, phi I t1 phi j t2 okay. Now since the if I not equal to j, so there are two cases. So if I not equal to j, then this quantity just evaluates to 0. Correct? Because how it happens? Because this has one creation and one annihilation operators, and this also has one creation and one annihilation operators. And what happens is that because these two commute, you can show that this is 0 when I not equal to j, and when I equal to j, this just becomes h bar over 2mi exponential minus I mi t1 minus T2. Okay, so this is for I equal to j. This is a simple thing. For I not equal to j, it is straightforward to check that the propagator is simply 0. And this, the essential reason for this to happen, this thing essentially happens because A1, A2 dagger equal to 0 is same as A2 dagger A1. Okay. So then if this is the case, then you can see that in case of, then when we try to do Wick's theorem, when we try to apply Wick theorem, then the contraction of phi 1 and phi 2 is 0. So not only this is 0, you can also show that the Weitmann propagator is also 0. Weitmann propagator is also 0 for I not equal to j. Okay. So this is the case, and then I mean with this modification, the Wick theorem straightforwardly applies also for multiple scalars. Can be generalized to two scalars Now what about, so if Wick theorem generalizes in this way, then you can see that the Feynman the Feynman rules also modifies suitably. So what do I mean by that? So because there are now two species, let's just now use two colors for Feynman propagators. So this is the Feynman propagator for phi 1. And this is the Feynman, let's say, this is the Feynman propagator for phi 2. Okay, and then the rule is that the rule is very simple. So let's, for example, let's try to construct the correlation function of, let's say, normal ordered phi 1 t1, phi 2 t1, phi 2 t1, and normal ordered phi 1 t2, phi 2 t2. Okay. So the diagrammatic rule will be simple. So firstly there will be 2 points again because there are 2 time arguments. And for from every point, 2 propagators come, but one will be green propagator because there is one phi 1, and one will be red propagator. Okay. Now because so the Wick contraction says that phi 1 phi 2 is 0. The Wick contraction of phi 1 phi 2 is 0, which means that the red line can only contract with red line and the green line can only contract with green line, which means the Feynman diagram will have this form. And then the expression is simply h bar over 2m exponential minus I m1 t1 minus t2 m1 times h bar over 2m2 exponential minus I m2 t1 minus t2. Okay, so this is the way that the position space Feynman rules and all these things suitably modifies. Now what about frequency space? So frequency space is also the simple, apart from the fact that the propagator, so let's denote the propagator d Feynman ij with omega, which is simply the Fourier transform of the position space propagator, Feynman propagator. And you can Fourier transform it, and you can just simply show that this is simply h bar over I h bar over omega square minus mi minus I epsilon whole square delta ij. Okay, so this is how the things that we have discussed for single scalar will suitably modify, and then with this modification you can easily change whatever we have discussed for single scalars for multiple scalars. I mean, for this we are doing for two scalars, but if I and j index runs over multiple indices, this is also suitably modified. Now what about if I and j? So this brief this is how the concepts of single real scalar generalizes for multiple scalars. But what if the I and j index, let's do that. What if the I and j indices take continuous value? Okay, so if I and j indices take continuous value, from these expressions it's pretty clear that the only thing that will actually change is that the delta function, the Kronecker delta function, I mean, let's say the I and j take continuous value and we denote them p and p prime. So these are my continuous indices. So delta I just suitably becomes delta p minus p prime. So Kronecker delta, sorry, what I'm doing. Delta goes to Dirac delta. Okay, so this is the modification, and with this modification everything simply generalizes. So what do I mean by that? So in this case then the Lagrangian is integration over p, I mean let's say dp pi dot p square minus mp whole square phi p whole square. Okay, the Hamiltonian will become h bar, again integration over dp a dagger ap plus half. Okay, so we haven't they haven't said we haven't said how, in what range p and p prime takes value and all this thing, but at this point it's just some continuous set of indices. Okay, then this means that the frequency space propagators the frequency space propagator will simply become h bar over e square minus mp square and then delta p minus p prime. Okay, so this is how everything will suitably modify. But we have to this point, up to this point we haven't mentioned where the p and p prime, what is the range of p and p prime takes value. Now take a special case. Consider a special case where p and p prime takes value in three-dimensional real space R3. Okay, if that's the case, okay, so not just that, but we also consider, so this is one so this is one condition for the special case, and second condition for the special case, that in this case then let's say mp square is m square plus p square. Okay, so this p and p are, these are three-dimensional vectors. And we also demand to this special case. So if we then go to this special case, then what happens? Then the Lagrangian is simply half integration d3p phi dot p square minus m square plus p vector square phi p square. Hamiltonian would simply modifies in the same fashion, but the important thing is the frequency space propagator. Becomes I h bar e square minus this p three-dimensional vector square minus m square d3 p minus p prime. Okay, so for this special case this happens. Now you probably already can understand, we'll connect it later, we will connect it soon, that this thing is same as real scalar field in 3+1 dimension. How? So let's connect this idea to the real scalar field in 3+1 dimension. So real scalar field in 3+1 dimension is described by the following Lagrangian density. Okay, so it is described by the following, let's say, action. So we have d4x which is same as d4x phi dot means time derivative minus divergence phi square minus m square phi square. Okay, so the now way people we will arrive actually at the same formula. So the way people quantize this thing is first computing canonical moment, pi of x, which is del L del phi dot of x. And then in the same fashion, we impose canonical commutation. So equal time canonical commutation. So which is simply, let's take phi of x, pi of x prime is IH bar d3 x minus x prime. So these are now, so okay, let's write in this way, x vector, x prime vector, x vector, x prime. So these are the spatial vectors. These are spatial components. Okay, so this is the way. So you can see that the generalization is very simple compared to multiple scalars which we discussed. In this case, again, the Dirac Kronecker delta has been replaced by Dirac delta. Kronecker delta has been replaced by Dirac delta. Okay, now in order to connect to the previous thing, we do a very simple thing. We do some Fourier transform which is of this following form. So the scalar field with the spatial coordinate x and time t, we just transform with respect to the spatial coordinates. Again, these are all spatial vectors. And if we substitute it back here, so if we substitute it in this equation, so let's number the equations. So let's say this is my equation 1 and this is my equation 2 and this is my equation 3. So if we put 3 in 2, we will find the Lagrangian to be same as 1. Okay, check it. So then this is very nice, because this what we found is that we found that the scalar field in 3 plus 1 dimension is basically a continuous collection of scalar fields in 0 plus 1 dimension. A continuous infinite collection of scalar fields in 0 plus 1 dimension. Okay, but then also let's now focus on, let's try to write it in a covariant form. So let's now try to do it frequency space propagator again. So we do go to first frequency space and P space. So what is this? So then we are now focusing on this thing. X1 T1, X2 T2, and then we take Fourier transform with respect to both D4x1 and D4x2. Okay, I mean up to, of course, suitable this thing exponential I x1 dot yeah, let's write this. Let's write this exponent here properly. So exponential I e dot e1 dot t1 minus p vector 1 dot x1, and similarly exponential I e2 dot t2 p2 vector dot x2 vector. Okay, and if we do that, what we'll get? We'll simply get this expression. Why? Because we can first Fourier transform with respect to just spatial coordinates, and in that case, if we do that, we'll just get the expression for this multiple scalar expression. Okay, so the expression will finally become I h bar e1 square minus p1 square minus m square plus I epsilon d3 p minus p prime, I mean p vector minus p prime vector, I mean here p1 and p2, I'm sorry, p1 and p2, and then the d e1 minus e2. And this can be written in a covariant form. How? So let's say my p mu and my p upper mu is then this quantity is same as minus I h bar p mu plus m square minus I epsilon d4 p, now the 4 vector p, p1 minus p2. So also there is a 1 to index here, 1. Okay, so then we found how to get actually the expression of this propagators in the frequency space for 3 plus 1 dimension, just starting from this propagator of real scalars in 0 plus 1 dimension. And the strategy was very simple. The strategy is that if that in order to actually start from the canonical commutation, you replace this Kronecker deltas, you replace the Dirac deltas by Kronecker deltas, because now there is a continuous set of indices. And once you do that, and once you actually just integrate, Fourier transform with respect to just the spatial coordinate, then what you arrive at is just real scalar fields in 0 plus 1 dimension, a continuous collection of real scalar fields in 0 plus 1 dimension. And then using our knowledge from 0 plus 1 dimension and then propagators, we can do all the computation as we have done for, all the computation in 3 plus 1 dimension can be simply generalized to computations in 0 plus 1 dimension in the simple fashion that we have now a continuous collection of fields, and we have to sum over continuous collection of those fields. Okay, so in the next lecture we will come back to this issue again.